So now that we know how to write Lewis structure for covalent compounds, now we can use that knowledge to draw resonance of those Lewis structures and to determine the shape on a 3D space for that molecule. Basically, how does the molecule look in the real world, not on a piece of paper. So let's begin to do that. Let's understand first what resonance structures are. And we're gonna do that by beginning by writing the Lewis structure. So let's do PO4 3 negative or phosphate. So we're gonna have phosphorus, 4 oxygens, and 3 electrons, right? Because it's 3 negative. So we're gonna have 5 valence electrons plus 6 plus 6 plus 6 plus 6 plus 3. So remember, the charge is how many additional electrons you have. So when we do that all together, we're gonna have 24, 29, 32 electrons. The first one will be the center one. And based on symmetry, we will put the oxygens evenly spaced around the central atom. And we have to use 32 electrons, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We got 6 more to go. So we're gonna put, let's see what we can do here. Oh, 6 more to go, right? I was forgetting about that oxygen up there. So that would be 32. So let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So that would be the structure for phosphate, which is going to be P, O, 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 O. Because it's an ion, we will put it in there, and then we can put all the other electrons around it. And that would be the Lewis structure for it, right? But we already know how to do Lewis structures. What we are trying to learn is resonance. So what is a resonance? A resonance is going to be nothing more than a different way of doing this with the same number of electrons. And we're going to say that it's a resonance by doing a double-headed arrow. So what we're going to do in this case is going to be, we're going to start with what we already have. So I'm doing exactly the same thing we have on the right side, and then I'm going to modify it. So a resonance structure will be, we can eliminate these 2 electrons, and we can put them in between these 2. Remember, a line is 2 electrons. That would be a possible resonance structure. Another resonance structure could be something with 2 double bonds in there. So something important to notice here. These oxygen have 8 electrons. This oxygen have 8 electrons. This oxygen have 8 electrons. Remember, the line is 2 electrons. and this oxygen have 8 electrons, 2 lines, which is 4, and 2 more pairs. But the phosphorus have 10 electrons. And you probably say, yeah, there's something wrong with that. That's not like a noble gas, right? However, there's a rule. When you go to the periodic table, you're going to have period 1, period 2, period 3. Any element that is on period 3 or below can have more than 8 electrons around it. So for the same reason, it's super important that the oxygen only have 8 electrons because oxygen is on group number 2. So any element that is on group number 3 or below, below on the periodic table, can have more than 8 electrons around it. And that's because on period 3, that's where the D block begins. And having D orbitals changes the rules a little bit. We're not going to go deep into why, because we don't go that deep on this course. So let's do another resonance. Let's do the resonance for Cn negative. So I'm going to have carbon, and I'm going to have nitrogen and 1 electron because it's 1 negative, which means I'm going to have 4 valence electrons, 5 valence electrons, and 1 valence electrons, which is 10 electrons to play with. So carbon and nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. And that will be 10 electrons. If you notice, the carbon is okay, but the nitrogen is missing 4 more. So the way we're going to fix that is by taking these 2 electrons and these 2 electrons and moving it in there, and taking these 2 electrons and moving them in there also. In other words, we did this: carbon, triple bond, nitrogen, lone pair, lone pair. So there's 8 electrons in there, and there are 8 electrons in there. So with only 10 bonds, 10 electrons, I was able to provide each element with 8 electrons, the octet rule. And it's an ion, so brackets, -1, and then we're going to do a resonance. So the resonance is nothing more than moving electrons around. So what I'm going to do, I'm going to leave this the way it is. And let's see what I can do here. I can probably take the nitrogen and move one of the 2 lone pairs there. And that will give me 8 electrons there and 6 electrons there. So that wouldn't work. So as you notice, I'm trying to do a resonance by moving electrons around, but I have to end up with meeting the octet rule everywhere. So I will have 2 electrons, 4, 6, 8, 10, but the carbon is not happy. So that cannot be a resonance. So let's try something else. What if I take the carbon and I put these 2 electrons in between, and then I have this. Well, the carbon will have 8 electrons, so the carbon is happy, but the nitrogen will have 10 electrons. Nitrogen is on period 2, so nitrogen is not one of the ones that can have more than 8, so that wouldn't work. Nitrogen cannot have more than 8, so that cannot be a resonance structure. And if I continue trying, I'm gonna soon realize that this structure doesn't really have a resonance structure, or at least I cannot find it right now. It doesn't matter how I move the electrons, I cannot meet the octet rule. The elements are going to be short of 8 or too much more than 8. So this structure will not have a resonance structure. So let's try the other one. So you got to play with it to see what you can do with it. NO2. So I'm going to have nitrogen, oxygen, oxygen, and 1 electron because it's 1 negative. So 5 plus 6 plus 6 plus 1, that will be 18 electrons. So nitrogen, oxygen, and oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16, and 18. So if I do that with 18, this oxygen is going to be okay. The nitrogen is okay, but this oxygen is going to be short. So I'm going to have to do multiple bonds. Every time I come out short, I'm going to have multiple bonds. So I'm going to take these 2 electrons, and I'm going to move them in between the nitrogen and the oxygen. So I'm going to take these 2 electrons, and I'm going to put them here. So this way, the oxygen have 8 electrons, the nitrogen have 8 electrons, and the oxygen have 8 electrons. And I cannot have anything more than 18, so 2, 4, 6, 8, 10, 12, 14, 16, and 18. So I know that will work. So this will be a good Lewis structure. And then it's an ion, so -1. So can I do a resonance structure? So once more, I'm going to draw everything the way it was. Double bond there. And the question is, can I rearrange the electrons so it will be different? So this is nothing more than that. So I can take these 2 electrons and move them over here. So let's do that. So I'm going to take these 2 electrons and move them here. Well, that wouldn't work because then the oxygen on my left is short and the oxygen on the right has too much. So back to square one. I'm going to put those electrons back over here. But now what I'm going to do, I'm going to take these 2 electrons and I'm going to move them over here. So let's do that. I'm going to take these 2 electrons and I'm going to put them over here. But now the nitrogen doesn't have enough. So I'm going to take these 2 electrons and I'm going to put them there. So I'm going to take these 2 electrons and I'm going to put them here. That way the oxygen have 8 electrons, the nitrogen have 8 electrons, and the oxygen have 8 electrons. So a good resonance structure would be then that one where you have now the oxygen on the left side is a single bond, And the nitrogen on the right side is the one with the double bond. So the only thing we do is that the electrons on the double bond are changing places. In reality, if we were able to see the resonance structures, we wouldn't see this. We wouldn't see that. We would see like a combination of both, where you will have the double bond kind of alternating between the two of them. And in nature, we just get like an average of the resonance. So the resonance are a good way to draw a possibility so that we can understand it better. So with that information, you should be able to do resonance for these three structures. And when you do that, we will be done with the resonance concept. So now that we know how to do Lewis structures, now that we know how to do resonance structures, now let's see how that's going to affect the shapes of the molecules. For example, you probably have seen water in a lot of places looking like this, an oxygen attached to two hydrogens. But you probably have never seen this, an oxygen attached to two hydrogens. So the shape that water have in real life is this one, and we call this a bent shape. So that's what we're gonna see. If you give me a formula, and I can draw the Lewis structure, can I also draw it having the proper shape that we know is the real one in nature? So how are we going to do that? Really easy. We're gonna take, before we get there, let's do something first. Let's do some more practice with Lewis structures. So let's do oxygen difluoride. So 1 oxygen, 2 fluorines, 6 plus 7 plus 7, that's 20 electrons. So oxygen goes on the center. By symmetry, we put the fluorines there, and then we put 20 electrons on it. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So that would be the Lewis structure for that. And any 2 electrons between 2 atoms is the same as a bond. Any 2 electrons between 2 atoms is the same as a bond. So what we're gonna do here first is learn some concepts that we're going to need to get to the shapes later. So determine the number of electron groups. So what are electron groups? This is an electron group. 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 So basically the different areas. And this is an electron group, and this is an electron group. If you notice, I color it different from the other ones because they're different. In what sense? Determine which ones are bonding electrons. So the only ones that are bonding are going to be those two. Those are the ones that are bonding 2 elements. So the yellow ones are going to be my bonding, and anything that is not bonding will have to be my lone pairs. And then to get ready for what's coming, we're only going to be looking at the central atom. So the central atom, which is oxygen, have 2 bonding groups and 2 non-bonding groups, which is the same as lone pairs. What are they? What do we call these lone pairs? Because they're alone. They're not bonding to anything. They're only alone with the fluorine. So that's what we're gonna do. We're gonna do the Lewis structures. We're only gonna be looking at the central atom, and we're gonna decide how many bonding electron contains and how many non-bonding or lone pair electrons it contains. So let's do it with the nitrogen trifluoride. So for nitrogen trifluoride, we're gonna have one nitrogen and 3 fluorines, so 5 valence electrons plus 7 plus 7 plus 7, which is a total of 26 electrons. So nitrogen is the center because it's first, and then we're gonna put the fluorine around. And then we put 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. So that means that the nitrogen is going to be bonded to 3 fluorines. It will also have 2 electrons there, and then fluorine have 8 electrons altogether. So nitrogen is my central atom, and it contains 1, 2, 3 bonding, and 1 non-bonding, or 1 lone pair. So that's what we do. We draw the Lewis structure, we look at the central atom, and count how many bonding and how many non-bonding groups or pairs the molecule contains, or the central atom contains. Why is that important? Well, before we do that, go ahead and practice that. Do the Lewis structures and determine around the central atom, determine how many are bonding, how many are non-bonding. Once we understand that, then we can do the shapes. And the reason the shapes work the way they work is because if, for example, if I have ammonia, right, which is NH3, something like this, what's going to happen is these are 2 electrons. This is also 2 electrons. This is also 2 electrons. And this is also 2 electrons. So what happens when I put an electron close to another electron? They will repel each other. So when we talk about the shape of the molecules, is what final result we have when we have those bonds on the molecules, and the fact that the lone pairs are electrons and the bonds are electrons causes them to repel from each other. So they're going to distribute themselves in a 3D space in such a way that they will be as far away from each other as possible. So if I happen to have ammonia, which is, like I just told you, which is like this for my Lewis structure, what's going to happen, these electrons are going to try to repel these electrons, same thing here and same thing there, and you're going to end up with the nitrogen there, the lone pair up, and the 3 hydrogen being pushed down, creating something similar to a pyramid. And we call this particular shape trigonal, because there's 3 of them, pyramidal, which is the structure that you're seeing right there. And notice that it says that you're going to get trigonal pyramidal when you have 3 bonding groups and 1 lone pair on the central atom. So that's how we use this table. First, we draw the Lewis structure just like we know how to draw it. Then we look at the central atom and we say 1 lone pair. So 1 lone pair and 3 bonding. 3 bonding, that's going to correspond with trigonal pyramidal for the molecular geometry. Since all together we have 3 plus 1, all together we have 4 electron groups. Because of that, the electron geometry is tetrahedral, but because 3 of them are bonding and 1 of them is non-bonding, the molecular geometry is trigonal pyramidal. So from now on, whenever I ask you to draw ammonia, you're not going to draw this anymore, because now we know better. You will draw something like this. And that will be showing the molecular shape. So let's go ahead, and we're not going to do all of them, so let's go ahead and do a few more. Let's go ahead and do PF3. So that one is going to be something like this. And at this point, I am not going to put the electrons on the fluorines anymore because they are irrelevant. I'm only going to be looking at the central atom, which is going to have 3 bonding groups and 1 lone pair. So that's going to be also trigonal pyramidal. So it's going to be something like this. Let's do another one. Let's do SO2, or sulfur dioxide. We're going to have sulfur and the 2 oxygens. So once more, I am not even looking at this. There's nothing wrong with having those in there, but I just want to emphasize that I'm only looking at the central atom, which is going to have 1 bonding group, and even though this is a double bond, we only count this as 1 group. So it doesn't matter how many electrons you have between the atoms, that region only counts like a bonding group. The 2 of them are part of the group, so that's only 2. So I have 2 bonding, so bonding groups. It could be that 1, it could be that 1, or it could be that 1, but I only have 1 lone pair. So it's going to have to be that one there, which is going to be bent on the shape, which is going to look like something like this. So your structure is going to be sulfur, oxygen, double bond, oxygen, and 1 more electron. And it's going to be bent. So that's basically what you need to do. Draw the Lewis structure properly drawn, following all the rules. Determine on the central atom how many bonding groups you have, not bonds, but bonding groups, and how many lone pairs you have. And then look at this part of the table so that you can decide the molecular geometry and then draw it according to the example. So you should be ready to do this daily work. And once you do all of that, we can say that we are done with predicting the shape of the molecules. On the next and last section, we're gonna see why it was important to know the shape. And we're gonna see more even on a future chapter. So with that said, we are done with that. When we come back, we're gonna see, so now that I know that, how do I know that a molecule is polar or non-polar? Like you know probably from memory that water is a polar molecule. Question is, why? So when we come back, we will do that. So until the next time, see you soon. Take care.